So we're talking about translating from English to symbolic symbols. Remember, we'll use things like a lowercase p, a lowercase q, sometimes even a lowercase r, if we're feeling fun, to represent different statements that you'll usually declare at the beginning, so it's clear what you're talking about. So let P and Q represent the following simple statements. P is the statement a bill receives majority approval. Q is the statement bill becomes a law. Now, we don't really care about the legalese behind it. We don't care about really anything except can we translate certain statements into symbolic logical form. So if we have the statement, the bill receives majority approval, or the bill becomes the law. Remember, the or sign is like a V. It's the upside down of the and sign. You're just talking about P or Q there. The bill receives majority approval, or the bill does not become a law. You're just talking about either P or not Q, or possibly both, but the word or in math is the and or. So it's just P or not Q. You see the little squiggly mark in front of the Q, that's a tilde. And so that's how we can translate some basic statements, basic things into symbolic logical form. Our next area that we want to talk about are if-then statements. If-then statements are really interesting. Think about it like this. If all poets are writers, let's assume that's true. So if you're a poet, then you're a writer. Well, I just kind of gave it away there. If all poets are writers, and I go find me a poet, William Shakespeare is a poet, T.S. Eliot, let's say T.S. Eliot. I grab T.S. Eliot, I say, hello, Mr. Eliot. He doesn't respond because, well, he's been dead for a long time, so we're talking about him in theory. I grab T.S. Eliot, I say, this guy is a poet. Well, if he's a poet, then he also must be a writer, if it's true that all poets are writers. So what's really cool about if-then statements, they're just re-expressions of the all. All of the smaller set is also a member of the larger set if it's a subset. If the poet, set of all poets, is a subset of the set of all writers, then all poets are writers. Also, if someone's a poet, then they are a writer. It's pretty simple. If-then statements just kind of re-express that idea. What's interesting about them, we talked last time about the analogies between chapter 2, the set theory material, and chapter 3, all this logic material. And we said that the union in set theory is the or, the disjunction in logic. We said that the intersection in set theory is the word and, the conjunction in logic. And now the if-then statement is just our way of creating subsets. So the if-then statement is analogous to the subset idea from set theory. If the set of poets is a subset of the set of writers, then if you're a poet, then you're a writer. That must be true. What if I go the other way around? If I say, if you're a writer, then you're a poet. Is that correct? It's not automatically correct. It's possible, but it's not logically deduced from that fact. You can find a lot of writers who aren't poets. Stephen King, you could argue, is pretty clearly not a poet. At least not for the most part. To symbolize if-then statements, we're going to use an arrow. If P, then Q. P is pointing to Q. So P is kind of like a foundation you're building. Q is what you build on that foundation. And it's pretty much just that simple. So if P, then Q. Be very careful because we can get real tricky with this. We can try to mess you up, basically, screw you up. We call it the conditional statement. It's a condition. If you're curious, we'll never really revisit this, but the statement before the arrow is called the antecedent. The statement after the arrow is called the consequent. Probably we'll never see that again, but just an interesting idea all around. So let's say we have the two statements. P is the statement, a person is a father. Q is the statement, a person is a male. If you wanted to write the statement, if a person is a father, then that person is male, you could literally just write if P, then Q, P pointing to Q. Whether or not this statement is true is irrelevant. All we're saying is we can write it symbolically. If you went the other way with it, if you wrote if Q, then P, this translates to if a person is male, the Q statement first, then they are a father, which is pretty clearly not true. You can be male and not have any children. In fact, do you guys want to hear a pretty interesting fact? If you look at genetics, if you look at the science of genomes and all that, there's been a lot of research done, and it's believed that only about 40% of all males who have ever lived on the planet in history and today, only about 40% of them actually have any children, any biological children, which is kind of interesting. It suggests that more than half of males are not breeding, and there could be any number of reasons for that. For females, I believe it's a good deal higher. I think well over half of all females have children at some point in their lives, historically or today. Again, that doesn't say you have to, you don't have to, it's whatever. It's just some interesting little facts. What's another thing you could symbolize? If a person is not male, then that person is not a father. Well, we're bringing the negations of those statements in, so we need to bring in the squiggly line, the tildes. So if not Q, then not P, is how you'd write that. That's how you could write it out a little bit in English. What's really cool is if not Q, then not P. If P, then Q is true. If not Q, then not P must also be true. This is called the contrapositive, and it uses a logical form called modus tollens. Again, don't worry about that. I'm just a little bit of a logic nerd. I sit and I study this stuff. Why? Well, because sometimes Minecraft gets boring. I play a good deal of Minecraft, even though I'm a 31-year-old man. Why do I play so much Minecraft? Well, gosh, it's just a lot of fun. It really is a good nerd game, and I'm a little bit of a nerd. So anyways, so you study logic, you learn new things. And that's kind of the motivation behind this. Here's the thing. How many of you have ever been in an argument? I would imagine pretty much everyone on here. How many of you have ever been in a Facebook argument? If you're under 21, Facebook is a social media website that you probably have never used or heard of before. How many of you have ever gotten in an argument in Instagram comments? Probably not so much. TikTok, I don't really think you really would get in an argument on that. But when you get into an argument, people will often attack each other in order to disprove the other person's argument. For instance, if you're a big supporter of a given presidential candidate, who cares who it is? Someone who doesn't like that candidate will just say, oh, you only voted for him or her because you're stupid. You didn't get an education. Or, oh, because you're super rich. That's the only reason you voted for them. Or You're very poor. That's the only reason you're voted for. None of those attacking the person making the argument, not a single one of those tell you why you shouldn't vote for that candidate. That has nothing to do with it. That's the person making the argument. You have to separate the person making the argument from the actual content of the argument that they're making. And if you're truly interested in having a discussion about something and having even a debate about it, you only attack the content of their argument, not the person themselves. In fact, that's called a fallacy. That's an ad hominem or a genetic fallacy. So it's very important not to just jump out at the person themselves making the argument. If I told you, if I had a friend, and look, everybody knows this guy is terrible at math. Every time he works a math problem, he gets it wrong. Let's call him Jethro. I have no idea. I just made that up. Let's say Jethro comes up to you and says 2 + 2 is 4. Is Jethro wrong because he's been historically bad at math? Is he wrong? Does 2 + 2 = 4 have anything to do with Jethro's background as a human being? No, 2 + 2 is 4 because it is logically, objectively, truly correct. It has nothing to do with the person saying that 2 + 2 is 4. So you have to separate the person from their argument. And I promise you, nobody does that. Almost everybody, you watch any presidential debate, it just becomes a clown show that's just not even really worth watching because all they do is attack each other as people, as human beings. It has nothing to do with logic. So it's hopefully we can express some ideas to you concerning logic and when is it important, why is it important. Now, what we're going to do is we're going to look at some different ways you can say if P then Q, different ways you can make an if then argument, even if you don't realize it. Every single one of these is if P then Q whenever you write it down in symbology, in logical symbols. So clearly, if P then Q, that's straight up definition. But what's interesting is it's not always whichever letter comes first is the letter before the arrow. This one says Q if P. So the Q comes first, but the condition is still that P needs to happen. Thus, P is pointing to Q. P is providing the evidence for Q, even if you rewrite it in this order. So for the statement P, a person is a father. Q, a person is male. A person is a male if that person is a father. All they did was rearrange it a little bit. They played around with it. But logically speaking, P is still the thing providing evidence for Q. A popular word is sufficient. P is sufficient for Q. What you're saying is that the statement P provides enough evidence for the statement Q to be upheld, to be logically correct. So if I say P is sufficient for Q, that's just another way of saying if P, then Q. P is pointing to Q. What's interesting is if you use the word necessary, you actually need to flip-flop things. You need to flip-flop them. The statement if P, then Q can translate to Q is necessary for P. Being a male is necessary for being a father. Again, we're not talking about whether or not that's true. We're just logically creating symbols out of everything. So the word necessary kind of flip-flops the letters, if you will, which makes sense because if one thing is sufficient for another to exist, then for that first thing to exist, it needs to be supporting something else. Thus, the thing it's supporting necessarily has to exist for the thing it was supported on to even exist. It's kind of weird to see it that way, but you can kind of see from the example how that works. You can use statements like only if, P only if Q. The word only also kind of makes things a little funky. Only if Q, P, that's still if P, then Q. So trust me on this. It looks confusing, and you better believe they can try and mess with you on this stuff. They can try to trap you in a semantic trap. But at the end of the day, you have to think about it. Think logically. What is providing evidence for the other? That's what you got to know. Whatever is the thing providing evidence, that is the first value or the first thing before the arrow, the antecedent. So up here, when you have a simple if-then statement, a simple regular one with a single arrow, we call that a conditional statement, that P is conditional for Q to exist. However, if both of them are a condition for the other one to exist, what we're going to call that biconditional statements. In other words, if we flip the order, if you have an if-then statement, and then you decide to flip the order, and it's still true, that's called a biconditional statement. And it's really not fancy. It uses a double arrow because it's saying P is pointing to Q, if P, then Q. It's also saying Q is pointing back right at P. If Q, then P. You're flipping the order. So the biconditional statement, basically you can reverse the order and still have truth come out of it. So that's what it is. So it's also called the if and only if statement. If and only if. If a person is a father, then that person is male. Let's say that's true. If a person is male, then that person is a father. That's not necessarily true. So when you have P being a person's a father, Q being a person is a male, that you cannot form a biconditional out of it because both directions have to be true. But down here, if we let P be the statement, a person is an unmarried bachelor. Q be the statement, an unmarried male. Q be the statement, a person is a bachelor. You can go both ways with that. When you do if P, then Q, a person is an unmarried male, or if a person is an unmarried male, then they are a bachelor. How many of you would agree that's true? Yeah, that's almost because the word bachelor and unmarried male are kind of the same thing, aren't they? They're different words or different concepts for the same idea. If you go the other way, if you do if Q, then P, if a person is a bachelor, then they are an unmarried male. That's also true, isn't it? Put another way, for this P and Q, you can go this way with it, and it's true. If a person is an unmarried male, then they are a bachelor. That's a true statement. You can go the other way with it. If a person is a bachelor, then they are an unmarried male. That's also true. Thus, you can use this, you can use the biconditional to basically make it easier, shorten how much you have to write out. They can point to each other and you can still get a true statement. Yeah. Is it not showing up over here? Oh, thank you for letting me know. See, I unplugged it, it's still showing it. So obviously something's going on with the overhead projector. Let me check it real quick. Oh, let's just bring that to my attention. Sorry, folks, the projector decided to stop working in the room. Give me 1 second. We're back up and live. So basically, say you had the statements P, a person is an unmarried male, Q, a person is a bachelor. The if P, then Q statement, if a person is an unmarried male, then they are a bachelor. That statement is certainly true here, we can tell. If you reverse the order, if Q, then P, if a person is a bachelor, then they are an unmarried male. That also appears to be true. So the conditional can go both ways. The arrow can go either direction and still produce a true statement. So we will just simplify our lives and say P if and only if Q. The arrow points both ways. That's also a true statement. If either of these fail to be true, then the biconditional is false. So if this way is true, but this way is false, the biconditional is false. It's got to go both ways. What's interesting about that, if you go back to chapter 2, set theory, the biconditional is the same thing as set equality, meaning I can set the two things equal to each other, the two sets. So in this case, the set of all people that are unmarried males and the set of all people who are bachelors, those two sets are exactly the same. They have the exact same number of elements and the same elements themselves. Thus, they are equal sets, if you want to go back to chapter 2 terminology. In chapter 3, that just means that the biconditional can be true about it. So some very interesting stuff. Let's review that one more time. Because gosh darn it, I just think that's so darn important. So the biconditional is another way of saying, look, these two things are basically the same thing. We might be using different words to express the same idea. An unmarried male, you might call a bachelor. Now, maybe that's not completely true. Someone who's unmarried, but if they've been with the same person for 10 years, you might not quite call them a bachelor, even though they haven't married that person. But let's just say it is the case for simplicity. So, chapter 2, set theory. Chapter 3, logic. Some of our concepts. In set theory, we called it the intersection. In logic, we're just going to call it the conjunction, aka the word and, whenever you write it in logic. And it uses this upside down V almost as its symbol. So these are basically the same exact idea. It's really interesting how that works. If you have a good grasp of set theory, you can attain a great grasp of logic. Maybe I should have put this one higher. I'll put it above here. The negation in set theory, or excuse me, the complement in set theory, I'm going to use green. The complement in set theory, remember in set theory, that was when you put an apostrophe above the set, and you were saying everything that set is not, everything outside of that set. The complement then in logic is the negation, or the not, and it uses the tilde symbol. So the complement is the same as the negation / not / the tilde symbol in logic. Really neat stuff. Orange. We can talk about the union. No, you're supposed to be orange. The union. The union in set theory is the same as what we call the disjunction, the or operator, and that one used just like a standard V symbol. But then now today we've added 2 tools to this repertoire. Let's do blue. The if-then statement, or excuse me, that's not what set theory is. The idea of a subset in set theory is equivalent to the if-then statement in logic. We also called it the conditional. And remember, we used an arrow to represent it. Arrow. Everything's showing up here. Good. And then finally, how about purple? We can just talk about set equality, where two sets are equal to each other. Well, in logic, that's just the if and only if. The by conditional, it's called, and we use the double arrow. The two are pointing back and forth to each other. I've been really stressing this information. We've talked about it. We talked about it last time, this time. You know, this might make for a really good test question. I don't know. Maybe it would, maybe it wouldn't, but I'm thinking it would. So, potential test question here. Just keep that in mind. Of what? Power Rangers. You had the green Power Ranger, who was Tommy. You had the red Power Ranger, Jason. There was no orange Power Ranger in the original cast. However, each season of Power Rangers, they'd all be different. You know, they'd have new Power Ranger stuff. So there was some orange Rangers. The blue Ranger was Billy. I don't think there wasn't a purple Ranger in the first season, but it changed each season. So yes, Power Rangers is a very apt comparison. I like that. You guys don't want to know how many hours I've spent on the Power Rangers Wikipedia page. And I mean the actual Power Rangers wiki, its own website. You don't want to know because I don't want to share. And it would disgust you. It would disgust you. You would say, Josh, that's disgusting. So the if and only if statement. Here's some other ways to use the by conditional. P if and only if Q. That is probably the most common way. We're going to use, or if you go further down the rabbit hole with math, you're going to use if and only if like it's your name almost or your birthday. You're going to just see it all the time because what that tells you is you have to do a two-way proof in mathematics. We don't have to worry about that. Q if and only if P. Well, if the arrow goes both ways, you can say Q is pointing to P and P is pointing to Q. You can do it that way. If P, then Q, and if Q, then P, sure, they're going both ways, the arrow. And then a real popular phrase, necessary and sufficient. P is necessary and sufficient for Q, means the arrow goes both ways. Q is necessary and sufficient for P. You can do that. Even if you write things out in symbols. If you do the double arrow like that, it is the exact same as if you happen to put the Q first. It doesn't matter. The arrow's pointing both ways, no matter how you slice it. So it's pretty freeing to have that. So here's a nice little quick summary. These are really the 5 symbols that we're going to use. The tilde, the squiggly line, if you will, for the negation, the not operator. The upside down V for your conjunction, the and operator. A regular V for the disjunction, the or operator. The one-way arrow for the conditional, the if-then statement. The two-way arrow for the biconditional, the if and only if statement, or the necessary and sufficient statement. So a nice little summary of it. Again, nothing we haven't already discussed. So here's where things get real tricky. Parentheses just like when you're doing math, parentheses tell you something. Parentheses say, keep these things together. If I put parentheses around something, you better keep them together. Imagine if you had, let's use something other than purple. Let's use orange. -3 plus 5. What would -3 plus 5 be? 2. It's the same as doing 5 minus 3 if you want. Is -3 plus 5 the same as this? Not at all, not even close there, Pilgrim. The parentheses are telling me to do the 3 plus 5 first, then perform the negative. So the parentheses absolutely matter here. Parentheses will completely change your answer if you are not careful with them. Keep that in mind when we look at what we're about to do here. The parentheses are meant to group things together. So for instance, if you have two very, very simple statements, P is the statement, she is wealthy. Maybe you're talking about Jeff Bezos' ex-wife. Q is the statement, she is happy. I imagine Jeff Bezos' ex-wife is very happy. She's a billionaire now. Look, here's how it works. If you're a billionaire, how can you be sad? No, that's not true. Money does not make you happy. In the words of Paul McCartney, money can't buy me love. How many of you agree with that? How many of you agree with that? How many of you think money does buy you love or happiness? You can be honest here. It's okay. Raise your hand if you think, wow, that's okay. Hey, you know what? Listen. If you have ever been seriously broke, or if you grew up broke all the time, you didn't grow up with a lot of money in your house, that's not fun. So I won't pretend that having your needs, your basic needs taken care of and not having to stress about money, I won't pretend that that's not a real issue, because that is definitely a real issue. I was broke my entire time through college. I was, growing up, we didn't always have a lot of money. There's a lot of things I couldn't do because we didn't have a lot of money. So I won't pretend that having money, having a good, consistent source of income is not going to bring you some happiness, because it will. Let's just be honest. But there is a limit. I mean, once your needs are met and you have enough free time to do the things you want, you may not need a solid gold car. You may not need a $200,000 car. So there is a limit, but I understand that it's not fun having to worry about finances. It's definitely not fun. And this is something I'll talk about a lot, actually. You always hear like these Disney movie nonsense, like, you don't need money to be happy. You're right. I mean, you can be happy in any situation, but what's the old saying? You never see someone frowning when they're on a wave runner. So that's just kind of something to keep in mind. Anyways, that was a random tangent. It has nothing to do with anything, but I'm going to talk about it. And the best thing is, this is college. You guys are all adults. I could come up here and say every swear word in the book if I wanted to. Now, I personally believe it's unprofessional to do that, so you won't hear me do it, but I could do it. I don't have to censor myself like if this was in high school, but I do choose not to talk about certain topics that are unnecessary. So if I can say whatever I want. I could even come up here and share my political and or religious beliefs with you. But guess what? I don't think that's appropriate for a math class. It's unnecessary in a math class. How many of you would be like, yeah, we don't want to hear you come up here and tell us everything that you believe? How many of you would agree with that? Really? How many of you would like to hear about my beliefs? I'm not going to tell them. I don't share them with you. I've had an equal number of people tell me I'm liberal and conservative. An equal number of students tell me that. I've had an equal number of students tell me that I have all kinds of different religious backgrounds. So I always make it a point to where my students cannot guess anything I believe in, because it's not necessary in a math class. Okay, so anyways, complete tangent there. P is the statement, she is wealthy, whatever that means. Q is the statement, she is happy. Be ye careful. And this is going to be, nope, not that. 1, let's block all these answers. Let's deduce them ourselves. Let's translate the following symbolic statements into words. So let's think about it with how the parentheses in this first one. With how the parentheses are oriented, the parentheses are around P and Q first. So first, she is wealthy and happy. But then notice this big tilde in front of it, and it's in front of the entire thing. This suddenly changes the logical content a little bit. This suddenly changes the content of what you're saying. If you take all of P and Q first, then you negate it. You're saying it's not the case that she is both wealthy and happy. You're negating the entire idea of her being both wealthy and happy. Thus, we need to write it something like that. Notice down here, though, here, there's no parentheses around the P and Q. So the tilde only applies to the P. So you could say something like this. She is not wealthy because you're saying she's not P. But she is happy. The word but, remember, is another cue for the word and. And when I use it here, it makes it clear that the not is only applying to wealthy. The not is not applying to the idea of her being happy. Even though she's not wealthy, she's still happy. That is a different sentiment than what we talked about up here. There's a different sentiment entirely, excuse me. So she's not wealthy, but she's happy. And then here, your original statement, P or Q, before we not it, is she is wealthy or she is happy. But then you're negating that entire thing. So it really becomes, it is not the case that she is wealthy or she's happy. In fact, I'll put a colon there. It is not the case that she's a wealthy or happy. Now, for the moment, all we're doing is translating these into English. But whenever we get to truth tables, suddenly we're going to start to slowly see the content make sense here. Now, here's where things can get a little bit nasty. Look at these kinds of statements. It's hard to express them in English, that is true. We can bring a third statement like are into the mix. That's okay. What we're going to need to do is we're going to need to put parentheses around things so we know what goes where. Because in this case, you see parentheses around this first statement. Everything before the arrow then is the if part of an if-then statement. So Q and not P. If Q and not P, and then you can even put a comma to pause, then not R. So the parentheses link things together. That's a completely different statement than this. Look how it's still Q, the and sign, the not P, the arrow, the not R. They are the same thing if you just wrote them without parentheses. But by putting parentheses around this, you're grouping this thing together. Q, and if not P, then not R, whatever that translates to. These are two different things, even though if you didn't have parentheses, they would look the same. See, I dropped parentheses in both cases. Suddenly they look like they're the exact same thing. The parentheses, though, tell me what to group together so that they're not exactly the same. Again, right now, we're just making translations. All we're doing is we're translating between these. So let's see. Write each of these symbolic statements in words. Let's say P is the statement, a student misses lecture. Very bad. Q is the statement, a student studies. Very good. R is the statement, a student fails. So let's translate this thing into English. Well, first of all, in logic, the Q and not P are linked together. So it's if Q and not P, those get linked together, then not R. The comma kind of helps. The comma would be the arrow almost in a way. But now let's actually put this in. Let's see. If a student studies and a student does not miss lecture, then a student does not fail. We sound like the Undying Men from Game of Thrones, but there it is. If Q and not P, if a student studies and does not miss lecture, then a student doesn't fail, the opposite of failing. Does that make sense? Does that translation make some sense? It helps to, this is the most symbolic way you can write it. This is the way you can write it in pure English. It helps to write this first. You're half using English and still using P, Q, and R to represent your statements. So I think this is a good intermediary to help you make these translations. Let's try out this one. Q and, in parentheses, if not P, then not R. So there's the good middleman right there. So let's think. A student studies, that's what Q is. And if a student doesn't miss lecture, and I won't even use a comma there, then a student doesn't fail. So if you both study and if you don't miss lecture, then you won't fail. Maybe that's true, maybe that's false. Maybe you can study, go to every lecture, try really hard, and you might still fail sometimes. That happens. But you're going to do better the more time and effort you put in. What if we don't have no parentheses? What if parentheses go away? Uh-oh. Without parentheses, it's hard to figure out a guide. Let's go up here. Let's figure out what in the heck is this? Q and not P, well, if not P, then R. Wait a minute. Do I do Q and not P, then do the not R? Or do I do Q and not P, then not R? What in the heck, where do I do what? What gets grouped together? If you don't have parentheses, it's not so obvious, is it? You could go a couple ways with this. Does this not symbol go to all of it? Or does this not symbol only apply to the P? Great question. That's what dominance of connectives is going to do for us. It's going to tell us what goes where first. What is the most immediate thing, and then where does it go from there? The dominance of connectives used in symbolic logic is defined in the following order. The negation is the least dominant, meaning if there's no parentheses and you see a negation, the negation only applies immediately to the next statement, to the symbol right in front of it, and then it stops. It does not dominate, it does not keep going after that unless you happen to put parentheses around. So up here, we didn't have any parentheses. Here's a negation, but it stops with P. It does not extend to the rest of that statement. So it's the least dominant. It just goes right next to its neighbor, and then it says, all right, I'm out of here. The next most dominant things, the conjunction or disjunction, are equally dominant, meaning once you see them, after your negations have been outlined, then you can start to connect things via the disjunction or conjunction. After that, the conditional is the next most dominant, And then finally, the biconditional is the most dominant, meaning if you see a biconditional, it pretty much separates everything on one side from the other. And everything is grouped on the left of it, everything is grouped on the right of it. Dominance of connectives. Oops. I always do that. This sure looks like order of operations from, you remember PEMDAS? Remember that? Please excuse my dear Aunt Sally, parentheses, exponents, multiplication, division, addition, subtraction. Order of operations, when you're talking about numbers, it tells you where do I do the addition, where do I do subtraction. It's a lot like order of operations. You do parentheses first, just like you do in logic. The parentheses group things together. Let's see, we go till 11:45, right? Okay. I think I messed that up last time. I thought we went till noon for some reason in my head. So look at this thing. P, arrow, Q, and not R. Where goes where? How do I group them together? Does the arrow get, is it the most dominant? Oh, well, okay, let's see. The not R gets to be on its own. Then the next most dominant thing is this conjunction here, the up arrow, the upside down V. So that tells me that this being the most dominant, this is the thing that divides them in the sand. So it looks something like this. Everything after the arrow is grouped together. The and says it's Q and not R. Going further down the line, we've got a biconditional, we've got a regular conditional. The biconditional, the two-way arrow, is the most dominant, so it separates everything on either side. So we take P, we take if Q then R, that's its own thing, then we do a biconditional. Looking at this thing, I mean, if you put parentheses around it, right? If you started off with this, well, suddenly it doesn't look so good. You could start off with this, where everything after the and is in its own set of parentheses. But that's not what we started off with. We had no parentheses. Well, start with this. You have the conditional. That's the most dominant thing. That is going to split them. That's going to be the line in the sand, if you will. And so everything before the arrow is grouped together. Everything after the arrow is grouped together. This not here, this tilde, only applies to the Q. It does not apply to the rest of this, just the Q. So let's see here. Let's get rid of that. Let's get rid of that. Let's say you have the statement, three statements rather. P is the statement, I fail the course. Q is the statement, I study hard. R is the statement, I pass the final. Let's see if we can symbolize this. I do not fail the course if and only if I study hard and I pass the final. Well, let's see. If and only if is there. So I know my biconditional, my double arrow, is in play. Oops. Before the if and only if, I have, I do not fail the course. I do not fail the course. Failing the course is P, so I do not fail the course is not P. Then if and only if, I study hard, Q, and I pass the final. Now, this statement may not make any sense. All we're doing is translating it. That's all we're doing. And then because of dominance of connectives, the Q and R are grouped together after the double arrow. This tilde here only applies to the P. It's not P. All right, let's do part B. Let's move this up a little. Part B. I do not fail the course if and only if I study hard, comma, and I pass the final. Notice how if I just read these directly outwardly, I'm going to have the exact same thing. This comma here changes everything. A comma separates the two ideas. So I do not fail the course if and only if I study hard. So I do not fail the course if and only if I study hard, which is Q. By putting a comma there, that makes this a group. Then we have the word and I pass the final, which is R. So the comma tells me where to group what. So part B here, the second thing would look like this. It's completely different. The parentheses are around a different set entirely. So commas are going to be your guide. Finally, I do not fail the course if and only if I study hard and I pass the final. I could write that out like this. Dominance of connectives tells me that because this business takes place after the double arrow, this gets linked together. And there's no comma up here in the original statement. So it doesn't tell me to link things differently. The not P is its own thing. The not only applies to the P. Get out of here. Any questions on that? It's a little bit confusing, I'll admit. There's a lot of moving pieces. As you work some examples of it, though, it should make a little bit more and more sense. A comma tells me to group things on one side of the comma with against things on the other side of the comma. Don't go anywhere. Let's take attendance.